Greetings, everybody. Today we're going to discuss heat capacity as well as be able to solve for the heat capacity formula. So a few vocab words that deal with the units of heat include the first one, heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. So a little bit of water, and if we add some heat, it's going to change the temperature. Remember, heat and temperature are not the same thing and they are not proportional to each other. So that being said, the first vocab is called calorie, and I did not mess up on making that a little c. Little c, calorie, is the vocab word. Now, what you're probably used to seeing is the uppercase calorie. I'm going to make this a big C. The upper case calorie is what we call food calorie, and there are 1,000 little calories. So otherwise, I think essentially what they probably just did is just to save ink, and just instead of this, nobody wants to see that they had 5,000 calories on the end of the label. So we just change the unit, make the number look smaller than it really is, but it's really the same thing. So anywho, so you have a giant capital C calorie is a food calorie, okay? And it equals 1,000 little calories, in which we're gonna be using for this unit. We're gonna be using little calories. All right, so the SI unit for energy is called joule. And not the joule you're probably used to, what you're probably thinking of, but again, joule is another unit of measurement to deal with heat. And so this is the conversion factor. 1 small little calorie equals 4.184 joules. So I'm going to box that in because we're probably going to use that later on. Hint, hint, wink, wink, nod, nod. So a little calorie, 1 lowercase calorie, equals 4.184 joules. All right, so another definition. The amount of heat energy needed to increase an object by 1 degree Celsius. We're going to call that the heat capacity. Remember, heat and temperature, two different things, and they don't equal each other. So you can add a lot of heat and the temperature not change with one object, and you can add a little bit of heat and the temperature change drastically with a different object, because different objects can absorb heat at different rates. So, and it depends on how much you have of that object. So in addition to the object's composition, mass is also important on its heat capacity. So I always think of like a giant pool. When it's really hot outside, at the beginning of summer, everybody wants to jump in, and they find out the water's cold. Well, it takes a lot of heat to change the temperature of water. In addition to that, the pool is very, very big. So it's going to take a lot of heat to eventually change the temperature of that giant pool. Okay, so I have a little interactive here, and we're going to add heat with our imaginary Bunsen burner, and we have a different object. Now the material can be wood, copper, glass, silver, sodium, or water, and we can change the mass, and we're just going to keep the duration the same for all of our trials. And so let's heat this up. Let's heat this. Let's do a metal first. Okay. We're going to start with 20 degrees C, which is approximately room temperature, a little bit colder. And we're going to have 5 grams. So let's heat it up. In 3 seconds, holy schmoly, we added 150 joules, which is, remember, it's a measurement of heat. We added 150 joules out of the Bunsen burner, and the temperature rose drastically. It went from 20 to 145. Holy schmoly. Okay, so we're going to end at 145. Let's see what happens when we change the mass. Well, you guessed it. If we add the exact same amount of heat, the exact same duration, and the object is bigger, the temperature is not going to change as much because it's that much more. So you probably are used to this with adding things to the microwave. If you add a big pot of food or a big bowl of food in the microwave, it's going to take longer to heat. All right, that's easy to understand. Or it doesn't take longer to heat. It's getting the same amount of heat. It takes longer to change the temperature. Almost messed up on that one. All right, so let's do water. We know there's a drastic change for metal. If you remember, metals are great conductors of heat. That means they can absorb heat very fast and they can release heat very fast. So let's reset and let's do 5 grams of water. 3 seconds. Oh my gosh. We added all that heat, the same amount of heat as the metal, and we only went up 7 degrees. Can you believe it? Well, it's just like heating up a pot of water on the stove. It takes a while. Water has a very, very high heat capacity. It's one of the reasons why our planet stays within a moderate temperature. It doesn't have that crazy of swings if you really think about it, because those oceans absorb a lot of heat from that sun and help moderate the temperature around the earth. So let's see. All right, so 5 grams, we went up 7 degrees. Let's see if we're going to add twice as much mass. So let's see what happens. About half the temperature swing. So that makes sense. We have a couple of variables in which we need to utilize in terms of creating our heat capacity formula. So let's start putting all these together and start solving some problems. All right, so we're back to our page, and we just finished a little interactive to represent the temperature swings that you can get from different compositions, as well as some. For example, water has one of the highest heat capacities. So if you have a high heat capacity is water, and that means that you can store a lot of that heat without a lot of temperature swing. So remember, water has a very high heat capacity. What objects had a low heat capacity? If you have a low heat capacity, that means that you can absorb the heat you absorb the heat and your temperature spikes. You are not very good at storing that heat. Your capacity is very low for storing. So capacity is very low, and something that's very, very low would be indicative of something that's a good conductor, and that would be metal. So metals, again, good conductors of heat, bad storing of heat. Water can absorb a lot of heat without changing its temperature. Metals change their temperature very, very, very quickly, okay? So we're starting to get a little bit more specific here. And so if we have 1 gram, the amount of heat it takes to raise 1 gram by 1 degree Celsius, it's just like a calorie, but we're going to call that the specific heat capacity because it's being specific on the amount. Specific heat capacity. All right, so specific heat. Now, water, again, has one of the highest. Liquid water, ice and gas have different heat capacities, and we get 4.18, or you can be a little bit more specific, 4.184 joules for every 1 gram is raised by 1 degree Celsius. Same thing, if we're using American units, 1 little calorie is the amount of heat needed to raise 1 gram. That's why 1 gram's on the bottom, and then 1 degree Celsius is on the bottom as well. Okay. Now, let's get our, formula out and start solving some problems. All right, so we have the units in which we used, or the variables in which we used in the interactive. We used heat. Okay, heat equals mass times the specific heat capacity and then let me see if I can fix this. Oops, that's not mine. All right, let's get back in business here, times the specific heat capacity, and then the change in temperature in Celsius. I know that we just talked about kelvins in the last chapter. It had to be in kelvins. Well, in this problem, in this formula, it has to be Celsius. So, and then we have a change in temp. So we have, I'm going to say delta T in Celsius. Okay, so heat is measured in, we're going to use the letter Q. M is measured mass in grams. So let's put grams here just in case we get kilograms. All right, so again, Q, and then we're going to have M for mass. And really confusing here. And it's not your fault if you get confused because we're using a lot of letters over and over again. All right. Specific heat capacity is big C. And you're like, big C is calorie or big C is Celsius. And you're like, we're going to use C again, and we're going to use it as specific heat capacity. And then we're going to multiply it by its change in temperature. That's in Celsius. So Q equals MCAT is the formula. Now remember, if Q is positive, that means we had absorbing heat. So if Q is positive, then we have an endo reaction. And remember, if we have a negative heat, we're going to call that exothermic reaction. All right, so this is the first page of your problem set in which you are going to take the information that is at the top. Okay, so you have time, and you have 1, 2, 3, and 4 different compositions. You're going to plot them and then determine if which one has the highest heat capacity, meaning that its temperature did not change that very often that much compared to the one that had the low heat capacity, that in which its temperature did have a major swing. All right, and then we are gonna work on a couple problems. So let's get the first one going here. First ball rolling. All right, so again, we have our formula, Q equals MCAT. Let me see if I can zoom in here. Let's go to A. All right, so our formula is Q equals MCAT. Remember, M has to be in, the mass has to be in grams. Specific heat capacity is provided right here. And then we have here's our mass. And then we have our change in temperature. That's going to be our delta T. Okay, so gold has a specific heat capacity of 0.129. That's considerably lower than water. Remember that water, you know what, let's make sure that we are using the right specific heat capacity. Remember the specific heat capacity of water is 4.18 joules, grams times degrees Celsius. So it's 4.18. The specific heat capacity of gold is 0.129. Remember, gold's a metal. That means it's a good conductor of heat. That means heat and electricity. That means it's not very good at storing heat. It's good at receiving and transferring. Receiving and transferring. So we have a huge temperature swing, okay? Huge temperature swing. We have 22 degrees room temperature, went all the way to 85, almost boiling, almost to the point where you're boiling water, okay? And just a little bit of, and 15 grams. So let's calculate our missing variable. So let me change my colors here. Gold has a specific heat of 0.129. How many joules? Now, remember, heat is measured in joules, are required to raise the temperature of 15 grams. So we have Q equals, we have 15 grams, 15 grams. We're going to multiply it by the specific heat capacity of that composition, 1.29. Don't forget your units, joules, grams, degrees Celsius. And then remember, delta T is the final minus the initial. It's very important that you do the final minus the initial. 85 minus 22. Let me get my calculator out. So we have 85 minus 22. 85 minus 22 times 0.129 times 15. All right, so our Q should be 121.91 joules. Okay, 121.91 joules, and that should be our heat. Let's do one more. So that one was just like, oops, I'm sorry, we forgot to do number one. Finish number one. All right, so since it's a positive, is it endo or exo? Did it gain heat or lose heat? Well, the gold received the heat, its temperature went up, so it is positive Q, so it's going to be endo. Remember, if it's positive Q, it's endo. If it's negative, it's exo. Let me box in my answer to make it easy for the teacher to give me a good grade. Let's see if we can find a different. What is the specific heat? Beautiful. So number 2. We're actually going to find the specific heat capacity. An unknown substance, we don't know what it is, has a mass of 100 grams. Beautiful, it's in grams. Beautiful, it's absorbing. It's very important that you understand the word absorbing because we need to know if it's going to be positive or negative. While undergoing a temperature increase, that means it went up positive. What is the specific heat capacity of the substance? All right, so we know that our formula equals Q equals MCAT. Now, we're going to put 1,000 joules in for Q. And the reason why it is going to be a positive is because it absorbed. Absorbing is positive, releasing is negative. It had 100 grams. Don't you lose your units on me. We're solving for C. And then it increased by 15. So we're going to put a positive 15 or a negative 15. Let's put a positive 15 degrees C. Let's rearrange the formula. Remember, C is by itself. We have things on the opposite side of the equal sign. So we are going to move 100 down to the bottom, and we're also going to move 15 down to the bottom. So what we have here is now C is by itself. We still have 1,000 on the top, and we just cross multiplied and brought the 100 to the bottom and the 15 to the bottom. So let's look at our specific heat capacity. Remember, if you get a number higher than 4, it's probably incorrect because 4.184 is one of the highest that you can get. So let's do 1,000 divided by 100 divided by 15. Whew! We didn't get anywhere near 4. So we got 0.6666. All right. Oh, shoot. Mr. Murphy did not put your units, joule, grams times degrees Celsius. There we go. All right. You want to do one more? Let's do one more. Huh? All right. Ooh, number 4 is good. For number 6, don't worry about absorbs. Let's find something that's a tricky one. All right, what about number 8? I don't know. What do you guys want to do? All right, let's do number 8. It sounds tricky. They normally put the harder ones at the very end, right? If 335 grams, remember we have our, oops, dang it, we forgot to finish our problem. All right, so remember, for the one we previously just did, if it absorbs heat, it's going to be positive. So we had a positive Q equals endo. Yeah. So for number 8, we have Q equals MCAT. So M is going to be, here, let's do Q equals MCAT. All right, mass is going to be 335 grams. The specific heat of this substance looks like it's water because it's 4.18. 4.18 joules divided by grams times degrees Celsius. And, ooh, this one is a tricky one. If 335 grams of water at 65 degrees Celsius loses 9,750, it loses this much heat. Is it going to be positive or negative? It's going to be negative 9,750 joules. So since we lose heat, I automatically know it's going to be exothermic. All right. What is the final temperature? Remember, we have T final minus the initial. The initial temperature was 65.5. All right, so this one's going to be a tricky one. So 65.5, and I'm running out of space. All right, simple algebra. We're going to start consolidating numbers and then solve for T final. And it looks like I am running out of room. So let's consolidate the 335 times 4.18 number. So we have 335 times 4.18. So see if I can write small here. All right, so we have negative 9,750 joules. Let's wait for it to catch up. And then let's consolidate the 335 times 4.18. It's going to be 1400.3. And now we have our temperature final minus 65.5. All right, so how do I get rid of the 1400? How do I get rid of it? It's on the opposite side of the equal sign. The only way to move it, multiply it, and then cross multiply. So this is going to go down here. And so this is going to go down to 1400.3. And since I moved it there, I can erase it over here. Okay. Now, I'm going to run out of space here. So let's flip our equation just because I like the variable on the left-hand side. You know what? Let me just do this. Okay. So we get, oh, you know what? Let's just keep it on the same side. Minus 65.5. And then what is 9,000, or sorry, negative 9,750 divided by 100.3. We get negative 6.96. And how do we get temperature by itself? Our temperature final. Well, if we're adding on the right, I'm sorry, if we have if we're subtracting on the right, how do we got to do the opposite? So we got to add on the right. So let me write that in red. Let's add 65.5 on the right. That cancels. And then let's add 65.5. And we should get, sorry guys, I'm running out of room. All right, so we started with a negative 6.96 plus 65.5 equals 58.54 degrees Fahrenheit. All right. Does that make sense? It lost heat so that at the end of the day, so for example, you've got a piece of metal or you have water. So that again, you've got this example, you have water, it lost heat. It started with a high temperature and then it lost heat. So therefore the temperature dropped. Okay, you measure the temperature later, temperature dropped from, went from 65.5 to 58.54. Hopefully this makes sense. We'll be doing more problems shortly. Cheers, everybody. Bye.